All right, well, guys, I know that was a short break, but welcome back. And now I'm in OneNote, so I'm going to write some of these notes down for you. So remember, Millikan, the goal of this experiment, okay, the goal of Millikan's experiment, whoops, okay, let me get the pen working right. So Millikan, his goal was to determine the charge on the electron and answer a question, okay, that people had been wondering about. Remember, like 100 years ago, this is when they're trying to figure out the structure of the atom. So, they're wondering about the nature of charge. So is charge this granular thing where electrons have this elementary bit of charge? They all carry the same number of coulombs. So they're virtually identical. Electrons, mass, charge, everything's identical. Is that the case, okay, for charge? So that's Millikan's goal, okay? And what he did was he used this apparatus. So here we see parallel plates. That little tiny guy there is an oil drop. This here is called an atomizer. If you're wondering, that little spray bottle I spray at school with the little, it does a mist or it does a beam of water, like the little plant sprayer. Well, when you put it in the mist mode, that's called an atomizer. It's, of course, the drops aren't the size of atoms. They're quite a bit larger than a single atom. Okay, but we call them atomizers. I don't know why, but anyway, that's the deal. Anyway, the point is the drops are quite small. Way bigger than atoms, okay? Many trillions of times bigger than an atom, but still quite small. You need a microscope to see them well, okay? All right, so here's the deal. Oil drop, and the oil drop in equilibrium, okay, with gravity. So the electric field here looks like this. Okay, I'm going to draw the electric field lines. Remember how the parallel plate apparatus produces a uniform field. So this is the electric field, and it is uniform. Okay, now there's a voltage across the plates. So, here you attach your power supply to the top. There's your positive electrode. Here's your negative electrode. And so I'm going to use a rainbow color here. And there is a voltage. I call it VAB. We'll call this plate A. Call this plate B down here. Okay? So there is a voltage across the plates, and that's kind of crucial. Okay? All right, so let's figure out how Millikan did his experiment. And it's actually a bit controversial, the way he did it. It's not really the way we like to do experiments today, but you can't argue with his result. He got a very good result. So he was within 1% of the modern value in the end of the charge on the electron. So he did very well, all things considered. All right, so here's the deal. Before we look at the Millikan experiment, let's just look at parallel plates for a moment. And we're going to talk about the field between the plates. Because it's uniform, okay, I'm going to draw a little parallel plate. Oh, no, sorry, arrow. This is plus. Okay, and that's minus down there. And here's my electric field. Okay, pointing from remember, you always take the direction a positive charge would experience a force. Positive charge placed between the plates will be attracted to the bottom plate and repelled from the top plate. So what I'm going to do is I'm going to put a little tiny guy there. Let's call it Q. And on purpose, I'm going to have Q starting at plate A and then moving to plate B. Okay? So he starts at plate A, he moves down to plate B, and the plate separation we're going to call DAB. Okay? So that is the separation of the parallel plates, the spacing between A and B. All right, Now, the voltage across the plates, I'll use the color blue for that. We're going to call VAB, okay? Now, what that means is the voltage all the way across from A to B, okay? So, here's the deal. We know that this charge Q is a positive test charge. We know, and I'll use the color red, we know he's going to experience an electric force in there, okay? Now, the deal is, okay, because the field is uniform, it's kind of like gravity the way it works. And so the work done, I'll go switch back to black here. Work done moving Q from A to B. Okay, so just consider this for a moment. We know that the work done will equal the electric force times the distance. Okay, theta is going to be 0. You know, work is force times distance times cos of theta while he's moving just straight down. So the force and the displacement will be in the same direction. So cos of 0 is 1, and so I can get rid of the cos of theta. Okay, and that's it. But here's the thing. We also know that the work will equal the change in electric potential energy, right? And we know that the electric potential energy will equal Q times the voltage. Okay, remember the definition of voltage is energy over your test charge, right? And so this little line that I've written here allows us to figure out how we can determine the force between the plates. Okay, so I'm going to go therefore Fe times dAb, so the work done equals Q times the voltage applied across the plates. So therefore the electric force is equal to Q times VAB over DAB. Now I'm going to put a box around that formula. It's a very important formula for you. Okay, that's how you figure out, okay, the electric force on charge Q, which is a tiny little charge. Remember, we're going to put oil drops in here. Those oil drops are going to carry some charge. Well, this is how much force those drops are going to experience because of the electric field. Now the voltage is easy to measure, right? It just comes from your power supply. And this is your plate separation, so VAB is the voltage setting across the plates. Okay, and DAB is the plate separation. All the way from plate A to plate B. Now, usually it's a couple of centimeters, right? Just not very much spacing between those plates. Okay, so anyway, this is your basic formula. Now Q is the charge between the plates, like not on the plates, but the charge that's placed between the plates. Now in Millikan's case, this is on the oil drop. I'll just put it in brackets because it makes more sense. On the drop of oil. Okay, so if you understand what I'm trying to say here, that equation in the box is extremely important. Okay, now I'm just going to say also note, because the definition of the electric field is the electric force divided by your test charge, Q, therefore the electric field between the plates, that Q that you see in the formula up there, now I'm going to write it, it's Q VAB over DAB, but then the whole thing is divided by Q. That goes away, and you're left with the voltage divided by the plate separation. Okay, and these two things, the voltage and the plate separation, super easy to measure. Okay, so sometimes we call this, I'm going to put AB. Okay, we call that the parallel plate equation. Okay, these two equations here that I put a box around. Okay, so epsilon is the field intensity, remember. Okay, now this is a vector. The direction of that depends on which plate is positive, the top or the bottom, right? It's always going to be away from the positive plate. So if the positive plate is on top, the direction is down. If it's on the bottom, the direction is up. But you can have these plates like this. You could have a plate, why do I keep drawing arrows? You can have a plate like this. Okay, well, here's your parallel plates. And let's say this side's positive and that side's negative. Well, your field then will be uniform and away from the positive and towards the negative, right? Because we always take what a positive Q would do, okay, for our fields. So anyway, that's what fields look like between plates. And this formula shows you how to calculate the field between a plate. All right, so now getting back to Millikan's experiment. His goal is to determine Q, okay? So in Millikan's oil drop experiment, he had an oil drop, okay? So actually, let's go up to it over here. He had an oil drop suspended in equilibrium, right? So it goes something like this. Millikan's experiment, you have your oil drop, and this is the free body diagram of the drop, and it's going to look like the one that was on the website. There's gravity pulling it down, and there's an electric force pulling it up. Now, what they meant to write, okay, they put a capital E. I don't know why they do that. We use epsilon in the textbook, not to confuse it with energy, right? This is the field intensity. So you get this, that the force of gravity is just equal to the electric force. Therefore, mg will equal Q, and here's the deal. They meant to write QE. Now, it's not Q capital E, it's Q epsilon. That's your field intensity, okay? Now, here's the deal. The field intensity is VAB over DAB, so really the equation should be written like this. Q times VAB over DAB. And I keep writing AB to remind you that we're talking about parallel plates here, okay? And this equation only works in those circumstances, okay? We have a uniform field between the plates. Okay, now solving for Q, just going to cross multiply, you're going to get mg DAB over VAB. And that, my friends, is the parallel plate. That's how Millikan, okay, that's how he worked out what the charge was on an oil drop. Now, he has a bit of a problem, okay? Voltage is easy. You just set your power supply to whatever. Okay, so what he did was he picked a drop, and then he adjusted the voltage until he could hold one steady, okay? And it depends on how much charge is on the drop, how much voltage it takes, right? Because we can see that here. However, the plate separation, no problem. And he built the apparatus, so like he just put a little spacer between the plates. He knew how far apart the plates were, no problem for DAB. G is 9.8, no problem either. The problem is determining mass. So the way he determined mass is, yeah. Anyway, it's beyond the scope of high school. Okay, he used something called Stokes Law, where you have a drop of oil and it falls. So you let it fall, and as it falls, there's some drag. Okay, because of air resistance, and then the air resistance, like, remember, he's trying to measure a tiny drop. So in order to measure its mass, what he did was density, which we use a Greek letter rho for, times volume, and not, so you don't think it's voltage. Here, you know what? Here, let me keep it simple for you. Density of oil times volume. Well, to get the volume, he used something called Stokes Law. You're never going to have to do this, okay? So forget that. Trust me, he had a hard time finding the volume of these drops, and his results were not very precise, unfortunately. And that's why the experiment was a bit controversial. Okay. Anyway, we'll get to that later. So you're not going to have to do that. You're always going to be given the mass. You won't even be given the density of the volume. You'll be given the mass in these questions. It's no problem. All right. So there you go. That is Millikan's deal. And let me skip to the results. Okay. What Millikan found, okay, actually, maybe before we get to the results, let's do an example. Let's just do a pretend experiment. And to do this experiment, okay, so here, I'm just gonna, I gotta be careful to give you correct numbers here. So, Okay, so what I'm going to do is I'm going to do an example. Well, actually, maybe I'll go back to the app for a second. Okay, so the app had 18 volts. All right. And it had a 500 nanometer radius. Okay. So he had this really amazing microscope, and he didn't really have a really amazing microscope, but anyway. This has a 500 nanometer radius, the drop in the question. So we're going to go with this. The plates are 3 millimeters apart. All right, so let me just take note of these numbers for you. Okay, so here's the deal. In one experiment, and I'm going to be switching back and forth. I'm just going to use the data given. So in one experiment, the voltage was 18 volts. Okay. The radius of the drop was 500 nanometers. I'm sorry, my pen is pretty much finished. I have to replace it, so yeah, my handwriting is worse than it normally is. Okay, and I will replace the tip shortly. Okay, the radius is 500 nanometers. Pardon me. The density of oil is 900 kilograms per cubic meter. Okay, and that's 900 kilograms per cubic meter. And what else do we need? Oh, the plate separation. DAB, I believe, let me just check the website again, was 3 millimeters. All right, so it's a virtual experiment here. I hope this works out, because anyway, we'll see. Okay, so I think we have everything we need here. We have the voltage, we have the plate separation, we have the radius, and we have the density. Okay, so let's first figure out the mass. Mass will equal, the radius of a sphere is 4/3 pi r cubed. Okay, so that's volume. And then the density is 900 kilograms per cubic meter. All right, so 500 nanometers is the radius, so that is a very tiny number. So 500 exponent 9 negative cubed. Okay, times 4 divided by 3 times pi. All right, I get a really tiny number there. I'm going to times it by 900. And I get 4.71 times 10 to the negative 16 kilograms. That's one tiny drop. All right, so that's fine. Okay, there's your drop. And now let's go ahead and find Q. So Q will equal 4.71 times 10 to the negative 16, right? That's the mass, times 9.8. Okay, times the plate separation, which is 3 millimeters. That's 3 times 10 to the negative 3. And then I'm going to divide that by the voltage, which was 18 volts, I believe, right? 18 volts, yes. All right, so it's 18. All right, and I get the result was Q is equal to 7.69. I'm going to keep all these digits. 7.6969 coulombs. Oops, times 10 to the negative 19 coulombs. All right, so you get this really tiny number. So that's one of his experiments. So he did that. There's one. There you go. Now he repeated this hundreds of times, and then he looked for a common multiple. Okay, or like a common factor. Okay, like basically the greatest common factor of these numbers. And what he found was the result. Okay, and then let me get to the results now. Okay, what he found was that all charges are multiples of 1.62 times 10 to the negative 19 coulombs. Now, that was his result. So now the modern value, slightly different. It's like 1% difference, 1.602 times 10 to the negative 19 coulombs. So he was a little high on his result, but this is the modern result, okay? And that, my friends, is the charge on the electron. So therefore, the charge on one electron is 1.602 times 10 to the negative 19 coulombs. Well, to be clear, negative 1.602 times 10 to the negative 19 coulombs. Proton, since a proton and electron are neutral, a proton would be positive 1.602 times 10 to the negative 19 coulombs, right? And therefore, all charges have to be multiples of these numbers. So what we do is we write Q equals NE, where E is the elementary charge, 1.602 times 10 to the negative 19 coulombs, and N is the number of excess or deficit electrons. Okay, so I don't know if that makes some kind of sense to you. So the experiment worked. He was able to find that electrons do have an elementary charge. He got a very good result. He did cheat a little. He had to fudge his data somewhat, but you can't, you sort of can't argue with history. He got the number that was very close. Like if you did a lab and got 1%, within 1% of the number, that's pretty good. But he did throw away a lot of data that he knew was outside of his ballpark. In modern science, we usually allow the data to falsify what we're trying to prove, so, but he had some crude apparatus, so maybe we can forgive him for that. So anyway, that's the conclusion of the experiment, okay? So the results, I'll put in a little box here. That's the result. Okay, you can see we got one drop here. Now let's take this result. Now that he's done hundreds of drops and he found the charge on one electron, so how many electrons is this then? Okay, so therefore N will equal Q over E. So let's take this charge Q and figure out how many electrons it was. So he got 7.6969 exponent 19 negative divided by 1.602 exponent 19 negative. And I get the answer is around 4.8. Now this is subject to errors. So you can't have 0.8 electrons. So therefore, approximately, electrons cannot be divided. So you can't have a fraction of an electron, right? So it's approximately 5 electrons. Okay, is the charge on that drop. Okay, so you see what happened there. Like he did this really cool experiment, really simple experiment, and he was able to determine the charge on these drops using those equations that I showed you. And then he was able to determine how many excess or deficit electrons were on each one. Okay, and determine that all electrons have an elementary amount of charge. You can't have a smaller charge than this. This number here is the smallest possible charge. And when something is the smallest possible amount of something, in physics we say it's elementary, my dear Watson. Okay, so it's the elementary charge. All right, I'm going to stop it here. So that is Millikan's experiment. We have one short lesson after this. It's actually the easiest one. I'm going to post it tomorrow, and then we'll talk about a test on Tuesday next week. Okay. So, oh, before I go, homework-wise, I just want to show you where we are. So homework-wise, we are now at lesson 5. Okay, so that's right there. That's Millikan's oil drop experiment. So we just went through that. We have 1 left. Then that's it. It's review, test, done. Okay. This last lesson we'll do tomorrow, and then that's it. We'll have a test next week, and we'll start something else next week. Okay, and we're on our march to, we have probably only 5 weeks left or so, 6 weeks left, and so we got a lot to do in the intervening time. So there you go, guys. So I hope you enjoy that, and I will talk to you soon, I'm sure. Okay, so have a good day, and we will talk to you tomorrow.